one right after the other.
Mm-hmm.
Yeah.
That's all.
All right. Okay, Emily.
Sure.
Sure. Thanks, Nat.
I mean, yeah, I'm ready to present.
Okay, good.
I'm in a humorous mood today. I must have
You
slept.
are?
Yeah, I'm just feeling like, I don't know.
Have you heard my Safeway joke?
Your what?
Safeway joke?
No.
Really?
Oh, I know this one.
Do you?
I think I know this one.
Yeah. This is like the only joke I have, but it's a pretty good one. Do you think it's all right, right?
I thought it was pretty funny. It took me a while
I
to
love
get
all
it.
jokes, so I'm excited.
Yeah. Okay, it's more of like a riddle. It's a riddle and a joke together. All right, you ready?
Okay. Yeah.
So, first of all, I have to like set it up because you all live in the East Coast, so you're unfamiliar with two important parts of the riddle. One is that Safeway is a grocery store that's like mostly in California and like maybe some other Western states, like maybe like Nevada.
We have them in Virginia.
Oh, do they really?
Yeah.
Okay, so then it's bigger. It's bigger than I thought. But okay, so Safeway is a grocery store, and you're young enough that you don't remember when you used to be able to go to the grocery store, and like nobody used to bring like their own bag. They would actually put your food like in a plastic bag, and then you know what I mean, and then you would take the groceries.
I
home
remember that.
Yeah. So
Okay.
here in New York, they just totally got rid of that this year, which is a great idea. Don't get me wrong, but back in the day, grocery stores used to be very happy to give you bags. So anyway, the joke goes, are you ready? How do you get an elephant into a Safeway bag? You're just supposed to say, I don't know, how do you do that?
I don't know how to do that.
Okay, thank you. So you take the S out of safe and the F out of way.
Just whatever you're thinking.
Wait,
Say it out loud.
there's no F in way. Oh, wait, that's funny.
Yeah.
I get it.
Yeah.
That's funny.
Yeah.
Oh, I fell right for it too.
Yeah. So share with your friends and family. You know what I
I
mean?
definitely will. Thank you.
Good. All right. And now we're going to hear about the Clayton and Regan synthesis of Epibatidine.
Took the words right out of my mouth. Yeah, the Clayton and Regan synthesis of Epibatidine. I had to practice saying Epibatidine by myself a couple times before I got it down. So Epibatidine. Okay, so what is Epibatidine? So it's an alkaloid found on the skin of these endangered Ecuadorian frogs, also known as phantasmal poison frogs. And they're able to secrete this poison on their back. So this is the structure of Epibatidine. And how dangerous is it, you ask? Well, Epibatidine has a structure. Its structure is set up very similar to another common dangerous drug, nicotine. And the way nicotine works is it binds to the acetylcholine receptors in the brain. And that's what makes it so dangerous. And Epibatidine, due to its similar structure, can do the same thing. And Scott, I'm going to try to remember this number right. It's like 1 cigarette is nicotine, and Epibatidine is 10,000 cigarettes. So
it's 10,000 times as strong. And also, do you see your problem in the Epibatidine structure?
Oh, there's no nitrogen here.
There's no nitrogen, and then there's a bigger, more sort of compelling problem.
Is this on the wrong?
No, that's actually okay.
So there should be a nitrogen here.
There should be a nitrogen there, just like there is in nicotine. And then Epibatidine is unusual in that it's chlorinated, but it's not a tetravalent chlorine.
Oh, yeah. Okay, I didn't draw these. I kind of just got them offline. So
are you kidding me? Oh, so
I drew them later on, but just for this step.
Yeah.
So this shouldn't be there.
That chlorine is not part of the ring. It's just attached to the ring.
Yeah. So it should be here.
Yes.
Okay.
That's correct.
I'm going to write a bad Yelp review on that. Okay, so
yes, please do.
I should have just drawn it. But anyway, minus the problems with this structure, it's 10,000 times worse than nicotine.
That's true.
So just to keep that in consideration. Okay, so now this is the whole reaction. This is what epibatidine should look like. So I'm just going to walk through each step. So the first step is a Diels-Alder reaction. I was proud of myself because I knew it was Diels-Alder, and then I went back and read it, and it said it right here. But the bonds are made right here, and these are the new bonds that form. So this is just bringing the structure together. And then the second step is hydrogenation. So it's hard to see, but right here is where the bond is going from an alkene to an alkane. And it's got really high yields, which is very good. And the first reaction was 85%, so those are pretty good. The reason that the double bond is removed on this side is because this sulfone group is electron poor, so due to resonance, it can remove electrons toward that like ring attachment. So it's easier for hydrogenation to occur on this side of the ring, where it's electron rich, or more electron rich than this side. And then the next step is reduction. So this is a really weird and rare reduction. And all it does basically is turn this sulfone group into a hydrogen. But it's got pretty low yield, which is not ideal and frustrating because you're basically throwing out more of what you make rather than keeping it and using it. The next step was the Heck reaction. So this is a reaction that Scott said we're going to talk about later on. So this is a palladium coupled reaction that replaces this hydrogen with this whole ring attachment. And what's important is that it's exo only, which is ideal for the structure of epibatidine because it's forgetting the word. Its structure shows only an exo attachment on this side.
Yeah, the Heck, I think this has come up before. Somebody else has one of these palladium catalyzed reactions. I don't remember who it is, but I talked to somebody else about this. That we'll talk about these carbon-carbon bond forming reactions that are catalyzed by palladium. Like, we'll do that next week. Like, I have a whole day just on that. So, but the Heck specifically couples aryl iodides, or aryl halides, I should say, to alkenes. So this is exactly like a Heck pattern.
It's like pretty specific.
Yeah, yep. And catalyzed by palladium metal, yep.
So, yeah, so that's what it does. And then the next step is deprotection. So what happens here is this group up here, this is a carbamate group, is replaced with the hydrogen through using hydrobromic acid and acetic acid. And what's interesting, so that's right there. What's interesting is that this also has low yield. So again, the reduction and the deprotection step both have low yield. So it's like this reaction isn't great. And what's evidence of that is that this whole reaction was published in tetrahedron letters, which Scott said is a place where reactions that don't work go to. So this is basically a step of like what not really to do, I guess, is how I interpreted it.
Yeah.
So it's not the best choice reactions compared to like Lindsay's or Beth's.
Well, I guess what I would say is that if their synthesis, so it's a journal where like less exciting results end up. Yeah.
Okay, yeah,
so,
that's a nicer way of putting it.
Yeah.
So then this is the mechanism for the deprotection step. So we make an oxonium atom appear using the hydrobromic acid, and then the oxygen over here steals, and then water is also added at the same time, and then the oxygen steals one of the hydrogens from the water addition, and we form, so we get now 2 OHs, and to get this to leave as methanol, this electrons here drop down and methanol leaves. So it leaves as methanol, and then the hydrogen is stolen with water, and the electrons are returned to oxygen. And then another water comes in and steals this hydrogen off of this end alcohol here. And then there's just a lot of protonation and deprotonation using water, if I did that correctly. So the nitrogen gets protonated using one of these protonated waters, and I just said it was a hydronium. That's how the nitrogen got protonated. And this will then be able to leave as carbon dioxide to produce the NH at the top instead of the carbamate. I think these last couple steps I wasn't super positive on, but that's how I went about them.
And do any of you remember, I think this has come up in the past too, that somebody had a Bach group as a protecting group on a nitrogen? Yeah. Lindsay did. So this is just like a Bach protecting group, which is also a carbamate. It's just that instead of a methyl carbamate, the Bach group is a tertiary butyl carbamate. And the tertiary butyl carbamate is very, very, very sensitive to being removed in acid. Like that, if you dissolve the T-butyl carbamate in acid, it'll be gone like literally in minutes. Whereas a methyl carbamate, you have to be like a bit more aggressive to get it to come off. Like you might have to actually like heat it to reflux for like a couple of hours to get the carbamate to get removed to expose the nitrogen. So, but these carbamates, whether it's, there's a bunch of them, I should mention. There's methyl carbamate would be like on the very sturdy end of the protecting group scale. T-butyl or Bach group would be, you just kind of like look at it wrong and it falls off. And then there are others too that there's one in particular called a benzyl carbamate, where the alkyl group in the beginning instead of a methyl group, it's a, if you remember, a benzyl group is a CH2 then a benzene ring, so it's one saturated carbon to a benzene ring, and those carbamates are removed by hydrogenation, which is kind of cool. So you just like put a little bit of palladium on carbon and a hydrogen balloon, and that removes the carbamate from the nitrogen. So these are all, protecting groups to mask a nitrogen, and then they all have like different ways that they get removed typically at the very end.
So is that why this has such low yield? Because it's so like sturdy on the carbamate here?
Yeah, I have a feeling if they used a different protecting group, they probably would have had a much higher yield of taking it off. Yeah. And, the whole point, right, of a protecting group, I think you guys must have talked about this with DJ, right? Protecting groups and like what their purpose is and stuff. The whole point of a protecting group is that it should be really, really, really easy to put it on and really, really easy to take it off and in high yields. So to have a protecting group problem like this is like, it really kind of, you know what I mean? It's like unfortunate, I guess. Let me get my phone real quick. Okay. I'll call him back. So, okay. It's a good one.
And that was my last slide. So this is the whole reaction again. And at the end.
Great. Great. Thanks, Emily. Cool. That was a good one. So, excellent. How's everybody? Is everybody doing okay? You seem very tired and like a little sleepy. All right, that's good. So I think next week I'm putting together like a little thing where each of you will have your own palladium catalyzed cross-coupling reaction to talk about what the coupling partners are, what kinds of catalysts, what sort of palladium, these are all palladium catalyzed reaction, but what kind of specific palladium species catalyzes it, and then maybe to dig up one example of using it in a synthesis. So it'll probably be pretty fast, but at least you'll see, get some exposure to what these reactions are and how they are used. I mean, I guess you're seeing some examples now anyway with the Heck reaction, and I think somebody had a Stille reaction coming up. Is that true? Either Beth or Lindsay? I can't remember. But anyway, but getting some familiarity with those palladium cross-coupling reactions, I think, is really good for you. So I don't know. That was very nice, you two. And the other thing I wanted to say is, so next week everybody begins, I think, doing topic presentations that are related to research papers. So I don't know if you have looked at sort of the guideline sheet that sort of describes what I think a good scope of what to present next week would be. But I think for everybody, but some people in particular, I think your presentation next week will be difficult because you're getting in, you're going to have to present data that you might be unfamiliar with, like where it came from and how it got generated. So I guess what I'm saying is maybe take a look at that sooner than later so that you and I can meet and talk about the data. If the paper is good, oftentimes you can kind of figure it out from the paper. But I know just from my own experience, when I read scientific papers, it is slow going. Like it takes a while to sometimes to understand what you're looking at and what it means. So that's going to happen to you too. So there's nothing wrong with that. That's kind of the point, I guess, is to start getting a little bit used to doing that. So, and the other thing I need, Lindsay, is your student ID number.
Oh, sorry. 704 3535 86.
Okay, got it. Thank you.
Yeah.
So, okay. Does anybody want to talk about anything else? I'm going to stop the recording.
Wait, Lindsay and I have ours.
Oh my God, what am I doing? You know what happened? I was in the like 2-person-a-day mode. That's why I'm like, oh, this is like, it's only 9:30, but that's okay. I'm sorry.
Like, I don't have to.
No, do it. I'm such a doofus. I mean, you know this already. All right.
Want me to go then?
Yes, please.
Okay.
Lord.